Okay, so good afternoon, everybody in Indonesia. And then for Rico, good morning, maybe now. Okay, so
Thank you.
today we'll have the third session of today's lecture. This session will give by Rico Visser, and he will tell us about the planetary formation and the simulation about it. So Rico, please, time is yours.
Thank you very much. And first of all, thank you to the organization for inviting me and giving the ability to give this talk. Oh, there's
Hello, Rico.
something to share screen. I see.
Okay.
Now I can share my screen. Okay. Can you all see this?
Yeah, we can see clearly.
Okay, great. Well, first of all, let me introduce myself for a bit. I'm Rico Visser, and I'm living in Amsterdam, the Netherlands. I work with Karsten Dominic. I'm a final year PhD student, so I'm actually promoting at the end of this year. And afterwards, I'm gonna look for a postdoc probably, or maybe do something else. I'm not sure yet. But now I'm still working on exciting stuff with, as I said, Karsten Dominic on streaming instability and pebble accretion. Here is Karsten Dominic. He's the director of the Anton Pannekoek Institute in Amsterdam. Furthermore, he has some people working with him also, and with me then, of course, that's the master student, or sorry, the PhD student, Kevin Lange. We're also working on planet formation. Then I have, then there's me. Then there is the master student Tom Konijn working with me on binary pebble accretion, which I will explain later what pebble accretion actually is. Then we have Mohamed Reski, also a master student at Bandung University, and yeah, he's working on actually the thing I'm talking about today, cloud collapse and n-body modeling. And then I have another student also a master student doing a double master program, actually pretty impressive, I would say. And he's also working on pebble accretion with me. So this is it's a small cozy group at the University of Amsterdam. Theoretical planet formation has been a bit pushed aside for the exoplanetary research group, but I don't think it's really a bad thing, because also that makes the group really connected and glued together. So I'm glad we are this small group working on exciting boundary problems in planet formation theory. By the way, if you cannot understand what I'm saying, or if you have questions, comments, remarks, you can always interrupt me, because I will be happy to hear you talk, because then I see that I'm still connected to the Zoom room. So please do so. Or you can raise your Zoom hand, but I cannot see that always that you're raising your hand, so you might as well interrupt me then. You can still hear me, right?
Yes,
we can hear you.
Great. Just checking. All right, so yeah, a brief background, because I'm perfectly aware of the fact that not everyone directly knows what I'm working on. So hopefully this will start relatively at the beginning, and will give you a small introduction to planet formation and the thing I'm working on in particularly, because I want to first start with just in general the modeling of an n-body cloud collapse, as we are doing right now in our group, where we actually use certain approaches that are not necessarily always justified to be entirely correct. So I want to have a discussion about that later on too. Hopefully you have something to say about that, because I'm curious to hear what you have to say. And afterwards I will give an application of this research, where we actually published a paper, the latest paper I published with Mark Brouwers, a collaborator in Cambridge. A couple of weeks ago, it was actually published on ANA, and I want to just discuss the results of that paper where we apply the embodying approach, which we discussed first. So I hope, and if you are not familiar with it, please say so and say where I'm going too fast or whatever. But I hope you are all familiar with the idea of a cloud collapse, a molecular cloud collapse to a star. At least how we think this happens, that you have a hydrogen or helium cloud somewhere in the interstellar medium, and this collapses due to the gravitation taking over from the pressure in this particular cloud. Then it comes closer together, so it contracts to the center of mass. It becomes a bit more violent because of all the temperature increase and all the molecules cramping up together, and eventually you come at this stage where you have mostly a star with a protoplanetary disk. It could also be the case that the star can actually take everything in and only a star remains, but most of the time you get a star with a protoplanetary disk around it, where gas and dust start to rotate in a flat disk because of the conservation of angular momentum, because all the material not falling onto the star, but next to the star will actually start to rotate like a pancake around the star, and will actually be the birth environment of planet formation, as we will see later on. Now there are a couple of course intermediate steps between these two last phases, but in general you would hope to see that this gas and dust disk around the protoplanet or around the star leads to some kind of formation of a planetary system. Yes, go ahead.
Yeah, hi. So sorry to interrupt.
No worries. You can always interrupt me if you want. So go ahead.
Okay, you talked about this protoplanetary disk. So is this disk a thick disk or it settled down as a thin disk?
Yeah,
how it goes.
That's one of the things we observe both, actually.
Okay.
So if we look through the telescope, let's say, for instance, sorry, there's a bit of noise here because a truck is passing. Hold on. Yeah, so we have most of the time we see that actually it's a plethora. So it's a really you can have really thin disks, but you can also have these flared, really thick disks where the scale height is gigantic and actually of the order of AUs, where you see the gas and the dust still hanging around at really long distances in the vertical scale height. So it's actually there are different cases we observe.
Okay, thank you.
Does that answer your question?
Yeah, yes. So does it depend, like if you are going to model this with n-body simulation, so how you are incorporating like the disk would look like, as you said, like you can observe both types of disk as thin and thick.
Yeah, so that depends indeed for the gas. If I would model the cloud collapse in the gas in particular, then I would really need to consider what the scale height of this disk is to ensure that, for instance, my cloud is in the scale height of the disk and not outside of it. So it's definitely some model dependent parameter that depends on the scale height of the disk. Yeah.
Okay. Also, how stable is this thick disk? Like if this protoplanetary disk is forming as a thick disk, so how stable is this? In the sense, like you might have know about this black hole accretion disk. So they first form the torus and then they settle down to a disk, right? So is it the same scenario can happen in this? Like first it is forming a thick disk as a protoplanetary disk, and after some time it settles down on a thin disk. Does that happen?
That's a good question. I cannot say for sure what the evolutionary process is of this time dependent, because of course there will be some inflow of material, and you might create gaps because this material will flow in and create kind of a torus or a donut shape of this disk, and eventually it will flatten out to a smaller disk or a flatter disk because everything accretes into the star. But I'm not sure how this happens over time.
Okay, yeah, okay, sure. Thanks. Thank you.
Thank you. Okay, so let's focus on this part, because this is the planet formation part. From this point to this point on, we hope to see that the planets form. I am personally also a fan of the, and I'm not sure how you think about this, but I'm also not excluding the possibility that already in this phase, that there are small planetary bodies formed already, because if there is a star formed here, there might as well also be planets that form already in the disk and that grow later on by other processes. But it's the consensus that this disk first forms, and afterward we have to form the planets from the dust and gas in this particular protoplanetary disk. So let's focus on this, and maybe we can discuss later on what the other possibilities might be for formation of planets. Okay, so the themes for today. How do planets form is a bit of a broad concept, of course, but let's break it up into smaller pieces. The important themes for today are the main planet formation theories that are available to us and that we actually developed over the years. What works to grow planets, at least in the sense that they are giving us a possibility to grow the planets within the disk, the protoplanetary disk lifetime. Then the numerical modeling of these theories, and then the application of M.Body in my latest work, which really is an application of M.Body, and where I will just discuss the results of this work, not necessarily the M.Body approach, but also the results of this work, because it might be interesting to see how this applies to research in general. Okay, so as I said before, the protoplanetary disk is assumed to be the birth environment for planets. This is just a gas and dust disk that is rotating with sub-Keplerian and Keplerian velocities around the star. And with sub-Keplerian, I mean that the gas has an extra pressure support, so it rotates slightly less than Keplerian, and the dust is just a solid, so it moves Keplerian. And the gas will actually then slow down the dust with a certain degree in the disk, which gives rise to really interesting dynamical interactions. But this is something that is more related to gas dynamics and dust dynamics in the disk. So we'll not discuss this in detail now. So let's look at the planetary growth ladder, because this is definitely something that might trigger your interest for the challenging field of planet formation. So if we start by aggregates, which are probably the size of a typical dust particle in your room. So if you haven't vacuum cleaned your room for 3 weeks, you might see these aggregates building up to dust, which is of the millimeter regime. Well, of course, you will not eventually get pebbles and boulders in your room, but eventually you will get these really large fluffy structures that starts to collect, and eventually you get these hay structures where you have these balls of dust. But in reality, in vacuum or in the interstellar medium, you might get to pebbles, boulders, planetesimals, protoplanets, etc., to gas giants. But this process is really, really long. It takes a really long time. And it's not some orders of magnitude you have to increase in mass, but it's actually 40 orders of magnitude you have to increase from an aggregate to a giant, to a gas giant. And this is really, you cannot even imagine, at least I can imagine how much mass this is you have to put in that aggregate to grow to a gas giant. So we really have to think seriously about how we can realize this process. So as you can see, from aggregates to giants, 40 orders of magnitude in mass. That's a lot. And then we have the constraint of the disk lifetime, which is on average, and this is really on average 3-4 million years. And this is really a maximum of 10 million years where you can expect the gas to be down from the disk. So actually the gas giants, where they formed their atmospheres and all the gas has been condensed, into planets, we have to assume that this happens as a constraint, but within 10 million years at max. So this is also a constraint we need to concern ourselves about. So we have to increase. Yes, go ahead.
So yeah, in your last slide, previous one, you told about that gas will slow down the dust. So I okay, so I believe the gas and dust both would be having different dynamics, and so they would be having different viscosities. So why just only gas is like they should interplay with each other, right? Like you
Yeah,
said,
yeah,
the
yeah.
gas slows down the dust, but dust should also have some impact on gas, isn't it?
Yeah, of course. Yeah, yeah, that's a good point indeed. But the dust is in general, the abundance of dust is much lower than gas in general in the disk. So what happens would be that the dust is negligible interacting with the gas, while the gas is really slowing down in a flow pattern, the dust. But if you have these very much compact and very high density dust regions, then you would actually see that the momentum exchange and the back reaction is very dominant from the dust also on the gas.
Okay, in the high density regions. Okay,
In the high density regions, yeah.
okay, okay, got it.
But in general, the dust is about 100 of the ratio in density as that of the gas. So that would be a negligible back reaction in general.
Yeah, so because there are like different density regions, the density is not
Exactly.
uniform
Yeah.
in that.
Yeah. Yeah.
Okay.
You would hope so, right? Because otherwise the star would never have formed from this collapse.
Yes, definitely. Okay. Yeah.
Yeah,
Thank
good
you.
question. Yeah, thanks.
Thank-
Okay, so these constraints indeed we have to consider for the formation of planets. Okay, so now we come to the main competing models in the consensus. I'm not saying that these are the absolute truth in terms of planet formation models, but I'm just saying these are the ones that I've seen a lot around, and these are generally accepted as the main competing models by the public and by the scientists working on planet formation. So there are two main competing models. So let's start with this. This is the first one, core accretion. You can form these aggregates and smaller planets in the disk by streaming instability or subsequent coagulation, where you actually collide things and they stick and they become larger and larger, and then you get these larger bodies. I will explain what streaming instability is in the next slide. Then you can go from aggregates to planetesimals by planetesimal accretion and pebble accretion or pebble accretion. From planetesimals to protoplanets, because then you have enough gravity and then you can, like a Pac-Man, sweep up all these smaller particles in the disk. Or you can accrete these planetesimals with these violent collisions where you actually grind everything down and take it in and grow larger and larger. And eventually you can just, because you have enough gravity, you can also start to condense or to pull in the gas in the environment, where you can create an atmosphere just like the giants have done somewhere in the history of the protoplanetary disk. So this is one way to grow these planets, or you can just directly, from gravitational instability of the gas, collapse from the start, actually very, very soon in the evolution of protoplanetary disk. You can collapse these gas structures where you have these indeed different densities at points where the gas becomes unstable. You collapse these giants directly from that. Only the problem is, where do you stop them? Because in this sense, if you would gravitationally collapse these bodies directly, you would actually have no halt in the collapse, and you would actually grow into a gigantic planet that might even be the order of the whole protoplanetary disk. So there's not much known about the process that would stop this in the early disk. So this is a bit controversial theory that's not believed by many, but it could be one way to form gas giants in the outer disk later on, where you have a cooler environment and the right conditions for gravitational collapse for some material in the outer disk. But these are the main competitors in forming planets at the moment. Okay, so core accretion goes from the smaller, as we saw, the smaller aggregates to planetesimals, because there are, if we look at them again, so here are the aggregates in the dust, where you might have some growth by these randomized motions where they stick together and you get these fluffy structures, as we talked about before. But eventually you come at the point where you have these barriers that really prevent you from growing further to larger bodies. And these are the drift barrier, where particles lose angular momentum. So the solids lose angular momentum in growth by the gas around in the disk, and then they spiral inwards, and then you never see them again. So you cannot grow larger, and they actually accrete onto the star. Then you have the bouncing barrier, which leads to just two particles like billiard balls colliding and just bouncing out, and you're now further than you were before. Fragmentation barrier, where you have these billiard bars just crashing in, and they make they break up into little pieces, and then you're actually worse than you were before. The electrostatic barrier, which is just on the really small scale, that you have these charged the same charges, and they just repulse, and you cannot grow from that. So these are this is pretty significant list of barriers that can prevent you from growing further from pebbles to boulders, which is meter sized. And now we have the streaming instability, which has been proposed relatively recent by Udall and Goodman, which is actually related to the question asked before about these solid to gas ratios in the disk. So if we have a local density of solids that's really increasing a lot and becomes actually on the order or larger than the gas density in the disk, then you can, by spontaneous clustering of these particles, I will show a movie later on, you can actually collapse these bodies directly to these planetesimals by gravity, and then you just skip this whole bridge of barriers in between. So this would be a way to form directly from the dust in the disk, from all these three here that are actually overdense in some region. We can collapse these bodies and we form these planetesimals. And this is indeed induced also by the back reaction of the dust on the gas, as well as the gas on the dust. But now the dust is the densest one, so it will actually push the gas towards Keplerian velocities, which sweeps up more and more particles, and you get this collapse. Is it clear so far? Yes, go ahead.
Yeah, so can you show your previous slide? Yeah, so as you said, from pebbles to boulders, we have to go through this barrier. So there are different types of barriers which are preventing them to go from this pebbles phase to boulder. So if the dust particles are going through this phase, so and I think like not all dust particles are moving, like some might might not go through this barrier, right? Or every dust particle is going through this barrier.
Yeah, well, every dust particle goes to probably one of these barriers. So if for instance, the drift barrier, the particles are really small, they are coupled to the gas and they will not drift very much inward to the star. If they get larger, then they feel the gas less and less, and they have sort of a threshold point where they actually drift the most towards the star because they are losing very much angular momentum to the gas. Eventually, they become larger even if they are able to become larger even, and then they don't feel the gas at all, so they don't drift anymore. But you first have to get to that stage, of course, to get to that point. But I think what you can definitely say is that the pebbles, so the centimeter to meter size, are definitely experiencing this drift barrier if there is gas in the protoplanetary relief, well, which there is. Okay, so for dust particles to move from this centimeter to millimeter phase to this boulder's meter phase, there should be some, I guess, minimum basic physical parameters they have to cross this barrier, I guess. Yeah.
Is it?
Yeah. So this is one of the problems that you can actually not this in general. It's not true for the whole disk because there's a Stokes parameter involved with this Stokes number, which actually determines how aerodynamically how much they drift these particles. So this is just to give you an idea. On 1 AU, this would, for example, be centimeter per meter particles, but there is definitely a threshold which you have to which you have to pass to be able to grow to meter-sized boulders.
Okay. Yeah. Okay. Yeah. Thanks.
Okay.
Yes. Yeah. Thank you.
More questions?
So there's explanation that you just said before, like the planetesimal formation time scale is about like dynamical time scale. So if I'm not mistaken, dynamical time scale takes about seconds. It's not even it's not even as long as hours or things like that. So it means that to create the planetesimal it takes less than 1 hour. Is it right?
So the planet, so in this sense, what I mean with the dynamical time scale is that it takes on the order of an orbital time of the planetesimal to form them.
Oh, all right. So I'm still confused what you were saying before. So can you say more once again?
So what I mean here is that the planetesimal formation time scale, which it collapses towards from the cloud towards a planetesimal, is of the order of years.
All right. Right. I got you. So yeah, thank you so
Thanks.
much.
More question? We have all the time in the world, so I'm happy with the questions because it means that I'm actually at least taking some of you people with me in being clear enough to ask questions. So please go ahead if you have questions or comments or remarks, whatever. Otherwise, I will proceed. Okay. So now we go further in the core accretion stage from planetesimals to protoplanets, which is actually this, if we manage to form these guys over here, these planetesimals, then we actually can think about, well, if we have a gravitational body that has enough gravity at least to sweep, that has a large enough gravitational well to pull particles in, pull pebbles in, or whatever, one of these guys here, or these even, or themselves in the vicinity. How would this work, and what can we expect to be there that helps us explain how these bodies grow further? Well, there are two ways we actually can think of that help us out here. The first is, well, actually I should start here because this is a more classical accretion model. Planetesimal accretion, you might have seen it before somewhere in courses or somewhere in your research. It's based on Safronov 1969 on his pioneering work on the protoplanetary disk, where you actually just have planetesimals or gas-free particles that are moving in a gas-free environment, and this body is moving in the disk, and it wants to accrete one of these bodies, and you get that the cross-section where you can release a particle or release a solid where it falls onto the body is slightly enhanced with respect to the geometrical cross-section where you would have that all these pebbles fall into the surface, only the particles here. So this is the geometrical cross-section would fall in. But now with the Safronov vector, you have this, because of gravitation of this body, you have this extension of the collision cross-section, which allows you to grow slightly faster than you would in the geometrical case. So it's, in this case, it sweeps up like this. And in this case, with the Safronov vector, it sweeps up like this. So they come actually from both sides, slightly further in the side direction. This is called the Safronov factor, this enhancement. But this also does not lead to very fast growth in general in the protoplanetary disk. So there's another way to grow them much faster, and that's called, and that's also recently new, 2010 actually, pebble accretion. And in pebble accretion, you have that these pebbles are, so these pebbles you saw before, this one, the smaller centimeter-sized marbles, or maybe fluffy pebbles can also be the case. They come in. This is the Hill. Does everyone know what the Hill radius is of a body? Am I still connected, or?
Yes, we can. They're still connected.
Okay, can somebody tell me what the Hill radius is? Anyone?
I'm not familiar with the term actually.
No? Is
Yeah,
there
yeah.
anyone familiar with the term Hill radius? Otherwise, I will.
Yeah. So
Go ahead.
correct me if I'm wrong. So
Yeah, of course.
it's a gravitational boundary surface within which if any smaller body will go, like will reach to this boundary or inside, it will be attracted by this center body, right?
Yeah. So indeed, it's the part of the story. Indeed. So I will just
Yeah.
quickly try to
Yeah, sure.
fill it. Add to this. So what the Hill radius is, so say you have this region. Oh, it's not really a circle, but bear with me here. And indeed, what you say that there's, let's say there's a planet in this middle, and there's a star over here, and you have this distance like this. Then actually, what the Hill radius is what if I would put a particle on this point somewhere on the Hill radius, then it would be exactly drawn with the same force towards the star as it would towards the body. So it would stand still over there. What that means is that within this region, everything would be drawn to the body, and outside this region, everything would be drawn to the star. Is that clear?
Is there a middle like a stable point where neither of where it is not attracted to neither of them?
Yeah.
Is
So
there-
these are the I always forget the name of these points. Can somebody help me? The Lagrangian point.
Oh yeah. I've heard that term. Okay.
Yeah.
Yeah, it's clear.
Okay.
Thank you.
Okay. Thank you. Are there questions furthermore? Because otherwise I will proceed with the concept of Hill radius in my explanation. Okay. Clear drawing. Yeah. Go away. Okay. So what I was saying is you have this Hill radius of the body. So in this region, everything will be attracted to this body because its gravitational well is actually extending all the way through here. And then the star takes it over and it will not be attracted to the body. And within this region, we would normally have that we have this, actually I'm going to draw it again now just for clarity. We would normally have without gas, what you see in the below picture where you have the Safronov factor, you might have some accretion, but in general, you get these two body interactions where you have that these, by conservation of energy, they just go away again and never come back, and then you don't have accretion. So this is the body that tries to grow. This is a body that wants to fall onto this body, but it cannot because gravity is making it difficult in the sense of the scattering cross section is conserving energy. But if you have gas in this disk, like in the case of a small particle, so planetesimals would not feel the gas in this picture. But if you have gas and small particles, so as you see here, away again. So a planetesimal would do the same thing as I said in this picture, where you actually have this and it will fly away again and you will never see it back. But these small particles, as we discussed before, will spiral inward because of this angular momentum loss to the gas, which actually leads to gigantic cross sections, much larger than the subpanel factor and of the order of a hill radius. So that's why the hill radius is drawn here, because the cross sections will eventually be, because this is the planet, this is the hill radius, they will be all the way over here, as you can see, because these are still spiraling inwards. So what you get is a very short growth time scale, and these planets will actually form really quickly if these, by the streaming instability, it's possible to form these planetesimals first, and then pebble accretion will take over to let gas rack and gravity conspire to get these really large collision cross sections to sweep up particles. So it's actually a Pac-Man that's constantly sweeping up these particles with a much larger cross section than its mouth alone. Okay. Okay, now we come to the streaming instability, because that's what I'm currently working on. I'm also working on pebble accretion, but recently I've been working a lot on streaming instability. So this is something I want to emphasize here. I don't want to talk about pebble accretion and streaming instability. I want to now focus more on the streaming instability, because this is an interesting example of this embodied collapse, cloud collapse, where you can actually see that it's really important to have embodied simulations to model physical systems in protoplanetary disks, because it's just very difficult and it's still open to a lot of interpretation of the effects you have to take into account, how we model certain tricks in sense of how we model collisions, gravity, etc. So it's a really interesting example, I think, personally. So this is a video of Rex and Lee, who's now at Cornell University, I think, where you actually can see a patch of the disk. It has been simulated with high resolution global simulation, which means that they are taking a very significant patch of the disk and they actually let it run where you see these clusters develop by this background reaction we discussed before. So first gas on dust and then the dust on the gas. So interchangeably they're working on each other. Hold on, my battery is saying that it's really low, so I'm going to check if my battery is in. Oh, now it's in. Yeah. Yeah. Okay. But this is the video. Full screen. Full screen. Full screen. It's not going full screen, but the point is clear, I think. So what you see here is all these things are planetesimals that are being formed from this background reaction in the protoplanetary disk. So you see, play it again. First you have only this gas and dust that are streaming, and these are interacting in the disk. But eventually you get this spontaneous clustering, and gravitationally the solids will actually clump together and form these planetesimals. Oh, sorry. Form these planetesimals from it. All these glowy things are planetesimals being formed. So you see that there are a lot of planetesimals that can actually be formed really quickly, on the order of years, in the protoplanetary disk to start with the pebble accretion process to form them even larger. Here, this is a really huge planetesimal. Here, some large ones. Yeah. So it actually, yes, go ahead.
Okay, so so okay, this simulation looks really good, like clumping of these dust particles. So you just include gravitational force in this simulation, or you are including some other forces, like let's say viscosity or any other parameters?
This is actually not my simulation, so I cannot tell you exactly what is used here, but I can tell you that the gravity is set on later.
Okay.
So first they let the clustering happen by this linear perturbation, because actually it's how do you call it? It's an instability, so an instability wave that also without gravity happens, that clusters these particles in the gas. Then you have this back reaction is included, of course, which we discussed before, where you asked a question about.
Yeah.
And then eventually they just put on gravity and you see these collapsing planetesimals coming up. So it's a hydro simulation. That's
Hydro
certainly.
simulation. Yeah.
Yeah, yeah.
Hydrodynamic. Okay. Yeah. Thanks.
Yeah.
Can you replay the video?
Yeah. Looks amazing, right?
Yeah, it's amazing.
Very nice. Yeah.
It's almost magical if you see all these
Yeah, like
bodies colliding and yeah.
Yeah, other cosmological simulations also I've seen, like MHD simulations. Those are also like really nice.
Yeah. It's really complicated because you don't know which effects are actually going on, and if you are doing the complete picture. But it's definitely a good start in pioneering these collapsing bodies and seeing what comes from that. Yeah.
Yes, definitely. Yeah, I agree. Yeah, thank you.
Okay, so are there any other questions? Okay, so now we're going to a bit more of the territory Reski and me are working on. And that is the final phase of all these bodies that are collapsing. We are not focusing on the global, so where we see all these are all hill radii also of the bodies. So this one is a really large one because they have large hill radius. These are much smaller. These are smaller hill radii. So the problem is with these large-scale simulations is that the collapse itself of these bodies cannot be tracked really accurately because simply the resolution is not high enough to go and track the body, the collapse of the body itself. So if you have formed such a clump, how would it collapse from that point on to actually a planetesimal? So now you are looking at the order of 0.5 hill radii or something that you can follow it, but eventually you just have to stop because you don't have the resolution anymore, and you're doing the wrong simulations to follow the last collapse phase. So here's where we actually do research about the final collapse phase of these bodies that formed with streaming instability in these global clusters. So we're taking one of these bodies. We're going to zoom in on that, and now we're going to do an n-body simulation because it's simply better to do an n-body on this cloud of particles. So now we're going to put it, just smear it out on its hill radius, and now we're going to see what processes we have to think about, what processes are important in the collapse of these final phase of these bodies, and we have to model it simply by an n-body simulation. Maybe you can think of collisions, gravity, self-gravity, maybe the effect of the star, etc. We'll come back to that. But the goals in this case are to obtain, first of all, the resulting core structure and the rotation. So what kind of spin will this body get afterward, after the collapse? Because these are all important parameters we have to check with the observations and see if they match. Because then we can say, well, we have found a consistent at least part of a consistent theory of planet formation. So these are the typical goals of tracking this last collapse phase, because we don't want to see them form only. We also want to see what comes from it. So what kind of properties do these bodies get? And then you have to get more accurate with locally these n-body simulations where you have all these effects taken into account in an equation of motion of the particles. Any questions? Yes?
Your goals, as you said, you want to study the core structure and the rotation after the collapse, right? So once this planet formation is happens, like the final giant planet has been formed, it rotates, and if they have a disk around the planet itself, that is also rotating. So since you are studying, so on what factors this rotation depends? or on what physical parameters, like from the scratch when this planet formation is happening. So it has angular momentum, viscosity, and other physical parameters.
You mean the planet that forms eventually?
Yeah, eventually planet has formed, so it has some rotation eventually, right? After formation.
Well, it doesn't have to have rotation, because if, for instance, you have some magical case, I'm not sure if it's realistic, but if you have zero spin from the start, you cannot have rotation eventually to collapse.
Oh, okay.
So I will come back to that, by the way, because that's actually the results of my my own research, which we can elaborate on that point.
Okay, so yeah, I'll ask this later. Sure. Thank you.
Yeah. Other questions? Okay, let's go ahead. So, as I said, you can make it as exotic and difficult as you want, of course. But in general, there are some typical things you have to consider in a cloud collapse. That is collisions between the particles, because they are not quantum tunneling tiny electrons, but they are actually pebbles and dust particles that feel each other when they come in close vicinity. So they actually, you need to take into account collisions. Self-gravity, gas drag is one of the things you can consider. We did not do this in the research I did, where I will talk about later, but this is something you would definitely need to consider in the cloud collapse in the protoplanetary disk. Then we have a co-rotating frame, because that makes it more easier. I do global, both local, so there are two different frames that should actually give you the same result, but are slightly different. Then you can ask yourself if you want stellar gravity, if you want pressure, if you want certain initial rotation and other external potentials, if you want to have a galaxy somewhere in the vicinity that affects your cloud next to the star, etc., etc. You can turbulence, all these things you can add. And now we get to the point, to the things I generally consider, and Rescue also generally considers in this collapse. Collisions, self-gravity, a co-rotating frame, and the global frame. Stellar gravity, I do consider, and rotation initially. Sometimes I do, sometimes I don't. I also do zero spin initial collapse. But these are in general the effects I take into account in my equation of motion for the collapsing cloud from TS0. And now we come to the, yes, go ahead.
Yeah, so I might have a very naive question. So you can incorporate these different interactions, right? So with different set of interactions, the simulation might differ, right? Or is it would be the same? Because
What do you
different,
mean?
like if I incorporate these interactions, like as you said, like there are different interactions. You can also add turbulence and viscosity and other things, but you are taking account of 5 interactions as you have shown in this slide. But in the previous slide, you stated many other interactions as well, right? So if we like with different set of these interactions, the simulation would differ or not, right?
Yeah, that's one of that's the idea. The reason why we don't take them into account is that the effect we found, that the mechanism we found is actually not even dependent on the interaction between the particles. So it's just an extra implementation of showing what might happen if you do this, next to that effect we found, which I will discuss later on. But in general, if you want to be really complete and realistic, then you have to take into account all these effects, and then n-body is not necessarily the right approach also to take, because hydro simulations might take care of turbulence better. But you have to, if you want to at least be close to what reality offers you, you have to look at time scales of these effects, and in how much they are actually applicable and how much they are negligible, because then you can scratch them away and then you don't have to use them. So for instance, if you have these dense regions where these particles, where these solids really are dominant, they can already look at the timescales for these turbulence eddies, like these turbulent motions of the gas, it might not be relevant because they are so cramped together already, these particles. No way turbulence is going to have an effect because the gravitational well is already strong. But it might also have an effect. So you just have to take a back of the envelope calculation and see which what estimates you get and what is relevant and what is not.
Yeah, okay. Yeah, understood. Thank you. There is a
More
question
questions?
in chat. Yeah, there is a question in chat for you. I
Can you
read it.
maybe
Yeah, I can read it. Is there is
Yeah,
a reason we have not included magnetic interaction?
yeah, we can include magnetic interaction, but in magnetic you mean, right?
Yes, yeah, magnetic interaction.
Yeah, we can include it, but personally I don't take it into account because I think it's too complicated for me.
Okay, so on that note, I do have a like, I'm not sure I have a comment. Like, even if we incorporate like that magnetic field won't be that strong to play any role, is it? Like,
Well, in these collapse, not, no, but I
in
can
these,
imagine that there are
no.
cases that it definitely is important, such as a cloud collapse on a molecular scale, for instance, like
Okay,
a
okay,
large
on molecular
cloud collapse.
collapse. Okay. On later
Yeah.
phase, it is not that strong to incorporate, but in the initial phase, in the molecular collapse.
Yeah, it might play a role in the balance of the forces in general. Yeah.
Okay, yeah, okay, thank you.
Okay. And then I wanted to tell you something about the challenges in the numerical model that are actually the most clear for me. So that's why I took two of them and really wanted to emphasize what the problems are in modeling a physical cloud collapse with a computer. First of all, typical amount of 10 to the 19 solid particles are embedded in such a cloud over a Hill sphere where you smear it out. So this is impossible to model by the computer. This presents a difficulty for us to really see a real life cloud collapse happening from our simulations. So we have to think of something to come close to reality, but we can never fully model such a cloud of 10 to the 19 particles. So we have to think of something for that. And then, as we discussed before, not all effects can be taken into account by n-body appropriately. Pressure and turbulence of the gas, for example, you can model it by some stochastic kicks in the equation of motion on a time scale, on a typical eddy time, for instance. That has been done before, but you can never accurately and correctly account for all these different effects with just n-body simulations. So that's why people are sometimes interested in magneto-hydrodynamical simulations, because it's more emphasizing the magnetic and the gaseous side of it, or n-body simulations where you're actually more interested in the physical interactions between the particles. But there has not been yet a model that can all take these effects all into account with just one approach of modeling a cloud collapse. So we have to start from somewhere, and body is a good way, but hydrodynamics is a good way if you want to model the gas and turbulence, for instance. Okay, so now I want to explain how I, in general, because I'm doing this these cloud collapses a lot, so I want to explain in general how I treat the different effects in the list of effects I showed before, where I go back to it. So I do collision, self-gravity, co-rotating frame, and a global frame. Then we have stellar gravity, and then we have the initial rotation of such cloud. But let's start with collision treatment, because as I said, 10 to the 19 particles, no way a computer can ever in a lifetime, or even in all our lifetimes combined together, model this. So we have to think of a way of circumventing this difficulty. So then we come to the inflated particle approach, which has been opted by Rijn et al. In 2010. So this is the same Hanno Rijn as many of you might know from Rebound, the N-body integrator, N-body solver that is publicly available. Really nice program, Rebound, sometimes a bit frustrating, but really nice in general. And this is the same person. And he says, Hanno says that if you have a physical cloud of all these particles, 10 to the 19 particles, and you have a certain mean free path of these particles, which means that they can travel a certain way before they encounter another particle and collide with that. So a typical collision time scale, you can also say it like that. Then you can say, well, I have the numerical, or sorry, I have the physical mean free path, which is n sigma, and physical times sigma physical, which is sigma is the cross section of a particle, cross section of one particle, and n is the number of all these particles here. And you have a certain numerical n times sigma. And what you can do is you can lower the amount of particles in the numerical way, blow up these particles with their cross section, and then conserve the mean free path in the numerical cloud, where you have much larger particles, but and a smaller number of particles, but you still maintain the same collision time in this sense. And this is the factor actually where you have to blow up the particle with to make sure that you keep agreeing with this physical mean free path. So you have to blow up the particles significantly because you have a lot less particles. And then you divide out the mass of the total cloud. Just divide them equally, because if you use one particular physical size of particles, the more it becomes more complex. That is what Reski is working on right now to correctly model this. But if you have one species of particles in this cloud, then you have this simple scaling factor, and then you have to blow up these particles, and then you have a lot less particles than you have here, of course. But then you are still modeling the correct system according to Hanno Rijn. And I do agree with him in the sense of overall you are maintaining the same, you are conserving the time scale of collision there. Is this clear? Are there questions about this? No questions? Am I still connected?
Yes. Yeah.
Okay. Good to know. Thanks. Okay. Then we go to the application of M-body gravitational collapse, which is the paper I published with Mark Brouwers in Astronomy and Astrophysics 3 weeks ago, I think now. It's called Prograde spin-up during gravitational collapse. Well, it says it, I think, in general, all, that it's a gravitational collapse, and that there's a prograde rotational component coming, popping up during the gravitational collapse. Does everyone know what prograde means, by the way? Can somebody explain to me what prograde is? Anyone? Okay, so prograde means that if you are rotating as a planet around your axis, that you're actually rotating in the same way as you are orbiting, such as the Earth, for instance. So the Earth is rotating around its axis in 24 hours, and it does that in the same direction as its orbits. If it does it the other way around, then it's retrograde. Is this a bit clear?
Yes, it's clear.
Okay, thank you. Okay, so let's start from the beginning. What we actually base this research on, which we've been doing in that article. So before we collapse a cloud, let's consider just a blob of particles of solids without gas. There are no interactions. Simple Kepler problem with a semi-major axis of its center of mass of this blob at T is 0, actually T naught. And these particles do not have any interaction with each other. So they are just simply following their own Keplerian orbits, circular orbits. And what you will see that if this cloud shears out, so that it's a cloud that's not interacting, so it's actually just a blob of particles that's been induced in a spherically symmetric blob. And now we let it just move. And now you see that all these particles are going to follow their own Keplerian orbits. And what you see is that the center of mass of this collection of particles is actually shifting towards the star. So you actually here you see that it becomes more and more an arc. And what we know from an arc is that the center of mass is located inward of the arc because it's curved toward a certain region. And if you have this blob here, it's the center of mass lies in the middle of this blob. But if you go inward, you see that the center of mass is now from this arc is going inward. Any questions about this? Because this will be the basis of what I will explain later on about this research. And this is then the star, the central mass. In this case, the star, but this is very general. So it could be a central mass in general, just the point. Okay, so these particles don't have any interactions. And now we come to the n-body problem, where we have perfectly sticking collisions. So actually when particles are moving toward each other, and we have one particle species here in this general n-body collapse, and we have the particles stick together, no gas here, just a simple collapse. This is over a Hill radius, we put all these particles together in the self-gravitating environment, where we use this equation of motion, the n-body gravity. And then this on a free fall time scale, so over on this orbital fraction of this cloud orbiting around the central mass, this cloud is going to collapse. And what happens is, because during the collapse, the center of mass, as we saw before, but this is over here, somewhere over here, as we saw before, this will collapse back into an object. It will shear out and then it will come back. The center of mass shifts slightly inward, and as a result, by conservation of angular momentum, we have that the angular momentum loss in orbital angular momentum, because you lose orbital angular momentum by the fact that the center of mass, or actually the semi-major axis, is changing of this clump of particles, the center of mass. That is actually has to be converted into spin of the object, so it starts to rotate. So it's a tiny center of mass shift, which leads to a lot of rotation, in this sense, at the end of the collapse. And what you have then is that that these clouds, in general, get too much angular momentum to form a single body, and overall you get, depending on the initial condition, you get binary formation, because there's too much angular momentum in the system, and it will actually fly apart and form a binary. Now, I have an animation, and I will for the animation we will work in the co-rotating frame, which simply means that we are traveling with the cloud at the point of at the evolution in time of this cloud collapse. So this is done with rebound. And there are a couple of things in this cloud. First of all, there's a star over here. So we are in the co-rotating frame, and we have a star located at the left of our co-rotating frame. Then we have a variable step solver for the interactions, for the gravity and the collisions and stuff. Then we have zero spin initial condition around the center of mass of this cloud. So the center of mass of this cloud is in the middle here. And then the initial spin with respect to the center of mass of this cloud is zero. So there's no rotation in this cloud. And this is what happens. So first you get this bar-like structure, then it collapses inward, and then poof, you get rotation. Like a little bit slower. Here you see the clustering of all these, because of self-gravity of all these particles. These are of the order 2,000 particles, I think, 2,500 particles. And then you see this bar-like structure. And then eventually it will just collapse on top of each other, like, and then it will fall in. Because of the collisions that are sticking, they all lose their energy in the collapse and they will fall in. And here the rotation starts to, the center of mass shift has now completed, which you won't see in this particular frame because we're not looking at it globally, but next slide we will see it. And now you have actually created from the orbital angular momentum a spin angular momentum for the collapsed body. Are there any questions, by the way, so far? Okay. So if we look at this in the global frame, where we actually look at it from the perspective of the inertial frame with respect to the central mass, so this is really the coordinate system centered at the central mass. And we have the central of mass of the cloud over here, which is shown by the black arrow that starts at T0 at this point. And we have two indicators of two particles we are tracking during the collapse. You can now see also zero spin disk. So this is the same simulation as we saw before. And then during time, we see these snapshots of the collapse. And what you see is that zero spin, and then it starts to turn, zero spin, and suddenly the blue particle is on the right side, which it started on the left, and the green one is on the left side while it started on the right. So it actually, starting with zero rotation, it has actually made half a prograde revolution in the collapse already to a solid body on a free fall time. And this rotation is typically of the order of barely forming a binary. So in this case it will be a solid object which is rotating pretty fast. But if you use Keplerian initial conditions where you have all these particles initiated on their own Keplerian orbits, then you will certainly follow a binary system because there is too much angular momentum being liberated in the collapse to form a single body. Any questions, comments, remarks? Yes, go ahead.
So every time if you start with a non-zero spin of these interactions, these collapse, so does it eventually end with a spin, or it might happen that even after the collapse, it doesn't have a spin?
No, it's zero spin always leads to the same. There are all converging simulations with a certain fixed number they collapse to in angular momentum.
So eventually after collapse, it will have a spin, even if it's starting from a zero spin.
Yeah.
Okay, yeah.
And this is because the center of mass, like what we showed here, like the center of mass of this, without interactions already, the center of mass is shifting inward, right?
Yes, yeah.
So also in this first region, you see that there is a small center of mass shift before the collapse finalizes.
Yes.
But this is enough to liberate a lot of angular momentum from the orbit into spin.
Yeah. Okay, thank you.
Okay, so let me see, where was I? Oh yeah, so the main findings, let's wrap it up to the conclusions. So the center of mass shifts inward of a system of particles moving on their own capillary orbit, so there doesn't even need to be an interaction. If this setup is modified to embody gravitational collapse, we get the following, namely that the difference in rotation you get from starting the collapse to the end of the collapse is scaling with the Hill radius with respect to the cloud's initial radius where you put it. So you can see that the Hill radius is the maximum where you can actually lead to collapse. Then you have the maximum spin, and then it drops very steeply to negligible spin if you put the cloud on a smaller fraction of the Hill radius at first, with respect to the Hill radius of the total mass of the cloud. And then we have that the scaling we actually find with this process in terms of the cloud mass with respect to the solar mass is the same scaling in rotation as seen in asteroids and planets. Tidal torque theory, which is a mechanism to explain galaxy rotation, where you have actually these external potentials that create the angular momentum for surrounding blobs of material. For instance, a galaxy that is rotating because of another galaxy pulling on it and creating a torque. This is tidal torque theory. And now we have a mechanism that actually can collapse molecular clouds also and create rotation from the process itself instead of from external potentials. And you have that this binary formation naturally follows from this mechanism because of the axis of angular momentum that is produced in this collapse by taking it from the orbit. So you can imagine that more massive clouds have the largest center of mass shift in the free fall time and also gain the most angular momentum. The question only is, in this sense, what is the relevance of this mechanism in cloud collapse in different astrophysical scales? We have discussed this, we have commented on this in the paper, but this is still an open question which we would like to investigate further. So these are the main results of this research, all done with an M.Body package of Hanno Rijn, including the interactions we discussed before. So that was actually what I wanted to say. Hopefully I was a bit clear in my explanations. Otherwise, please do say and ask questions and give comments on it. Thank you for your attention, and I would now like to start sort of a discussion panel. And I'm not sure how much time has passed, but yeah, let me know what you think. Thank you.
Okay, thank you very much, Rico, for the talk. So, is there any question from the participant? Okay,
Go ahead.
Go ahead.
Yeah, hi. So I'll ask the same question I was asking, and you said like you will answer once you shows the result. So you say in your simulation, and as you stated, even if we start with a spin 0, eventually it will end with a spin of final collapse. Okay. So what I am asking is now, on what parameters does that final spin will depend? Like, does it depend on initial angular momentum or the self gravity and other physical parameters? Does it depend? Because every planet eventually will form and it will have some different spin, like each planet. They don't share a same spin, right?
Well, yeah, that is a good question. So what we find, first of all, that in observations, we find that the spins of planets and also smaller solar system bodies is clustered around, let's say, 4 to 24 hours.
Yeah.
And that the direction is 80% prograde, 20% retrograde. So there's definitely a trend there that they are leaning towards a systematic prograde spin between, for the larger planets, for the gravitational bodies of the order of 8 to 24 hours. So that's one thing. So in general, you would expect these planets all to have some sort of common formation mechanism that leads to a clustering of these spins, such as the Earth 24 hours, Mars 24 hours, let's say Jupiter, I think 10 hours, Saturn 9 hours, something like that. All these are very, very close together, and there you have these tidally locked satellites next to it. So this would be in this way. I mean, the collapse, the angular momentum in this mechanism that forms from the collapse scales with t squared. So during time, if you do it on the free fall time, you have gained a t squared dependence on angular momentum, and which does depend on the initial condition, but eventually a small amount of retrograde spin induced during the collapse could lead to a prograde rotating body. So what I'm trying to say is that this mechanism definitely ensures a prograde bias of angular momentum buildup in a collapse of a rotational cloud.
Okay, yeah.
Because these initial conditions are all, I mean, you have, for instance, if you look at the retrograde initial condition of angular momentum, so it goes the other way, it all spins the other way around. You have a zero spin where it doesn't spin in the first, and you have a prograde. All these lead to, on themselves, fixed amount of angular momentum that doesn't change if you do the collapse again, but leads to one number of angular momentum. So it all converges to one particular number of angular momentum.
Okay.
Hopefully it answers your question.
Yeah. Okay. So, so I do have a might be confused a bit. So in your simulations, the spin you are getting at your final stage, that is retrograde, right? Sorry, prograde. Prograde.
Yeah.
Okay. So, I mean, there could be like possibility that at final stage we might get a retrograde.
Yeah, but then you have to start with a retrograde spin.
Oh, okay. Then I have to
Because
start.
then if, for instance, if you start with a significant amount of retrograde spin that it doesn't fly apart the cloud and that it still is able to collapse, then you have a region where you actually can expect it to be less retrograde. So it's still gaining prograde spin, but it just becomes less retrograde. It doesn't pass the 0 bar to prograde, but it just is slightly less retrograde.
Okay. Yeah.
And if you start with a particular amount of retrograde spin where you do pass the 0 bar and go to prograde, then you see that there's a bias to grow prograde spin, because then you start with a retrograde spin and after the collapse you have suddenly a prograde spin. This is a certain threshold in between.
Okay, so what like physical scenarios happening to overcome this retrograde and mostly favoring this prograde thing?
Yeah, you would expect that in general the randomized velocities at the start or whatever, if you have a molecular cloud, for instance, where you have all these molecules just by turbulence moving, or just they have a certain velocity component at the start, which should be very strongly retrograde if you want to have a retrograde rotating star or planet or whatever, what kind of cloud collapse you're thinking about. So in terms of physical scenarios, it should actually, if this mechanism, I mean, this mechanism is happening, right? If you are collapsing, you are around the center of potential, then your center of mass shifts inward because you slightly shear out first and then you collapse. So the center of mass shifts inward, and in general, it is the case that if you start with 0 spin, you get prograde rotation. If you start with prograde rotation, you get more prograde rotation. If you start with retrograde rotation, you get slightly less retrograde rotation in one sense. And if you start to retrograde rotation, negative rotation of what you build up during the collapse, you get maybe 0 rotation exactly. But there's always this bias towards prograde rotation.
So I guess like there would be some physical inbuilt parameter, like physical uh, thing is happening there, which is favoring this progress, right?
Yeah, yeah. Well, I mean, it doesn't even have to favor prograde, because if you have zero rotation, then you also get prograde rotation.
Yeah.
So you have to have a really strong retrograde rotation in able to
Yeah.
form something that has retrograde spin, such as Venus, for instance. Venus rotates the other way around.
Okay, so I guess maybe like if you can correct me. So if even if we are starting with this spin zero, and when this collapse and this clustering is happening, so the velocity vectors that are generating that time, they are prograde, and then that's why we are getting a prograde spin after the collapse,
Yeah,
right?
yeah.
Okay.
Yeah, as you can
Thank you.
see here, so first it looks that this is no rotation around the center of mass, so they are not rotating initially
Yes,
around the
yes,
center of mass. They don't have spin any
yes.
direction. Then it collapses, and suddenly you see this one in a prograde sense
Prograde
shifting.
sense.
So, and this one you see it shifting this one, this side, and then you have a prograde, half of a prograde revolution you see happening here.
Yeah. Okay. Yeah. I got it. Yeah.
Kind of magical, but also kind of makes
Yes.
sense that because of the
Yes.
center of mass shift, that it's liberated from the orbital angle.
Yes. Yes. Yeah. Yeah. Got it. Yeah. Thanks. Thanks a lot.
Thank you. More questions, comments?
Is there another question? Okay.
Hello, can you hear me?
Yes.
Okay, I have a question about this N-body simulation. Is there any difference between this method and body simulation with smoothed particle hydrodynamics in fluid simulation? Is it the same thing? And is there any key difference between them?
Yeah, that's a good question. And the key difference in my perspective is that I mean, SPH does handle these particles and these gas patterns in there as a flow prescription, where you use a grid of cells, where you actually have a certain resolution dependence, where you if you want to do this correctly, you have to have a really high resolution and to really how do you say it, make sure that these cells are comparable to the movement of your flow and to your particles, such that you can resolve the motion of your particles and flow correctly. And on these scales, these cells would have to be really tiny, and your resolution has to be really high to do this correctly at the end of the collapse. So it's less suited for these kinds of collapse, end collapse stages, because you're not looking at an equation of motion on particles, but you're looking at the properties of cells in your simulation, which the flow pattern and the particles also handled as a flow pattern have to go through, where you actually have to make sure that your cells are solving it correctly.
Yes, that's explained a lot. Thank you very much.
Thank you. But correct me if I'm wrong too. I mean, I'm not working a lot with SPH. I do have experience with people who work with it, and I read a lot about it. But it might also be another thing that's the key difference.
So I do have a question, kind of discussion. So in the chat, like someone asked, like, don't we incorporate magnetic field? So I guess it's very less. That's why we are not incorporating. It's not of that great magnitude. But I'm just curious to know, even if like very low magnitude is there of magnetic field, like, what if we include and do a magnetohydrodynamic simulation? So would that make any difference in the like final collapse, or would there be a different mechanism, or like, how would
Yeah.
the
So
result would differ?
my question to you would be, what would Because I'm actually not sure. So this is why the whole reason why I'm inducing these discussion panels. So my question to you would be, what would change and what would be the effects of these MHD introduction to these simulations?
Even I'm not sure, like magnetic field might play a role in the spin, probably.
I agree. It might play a role, but the question is then, how large are the magnetic fields of these, and how are they induced in this at the start of the collapse for these particular? Are they induced by the gas, for instance, or by the particles themselves?
Yeah,
How strong is the magnetic field,
yeah,
or is
yeah,
the star maybe even playing an effect? I'm not sure.
yeah, that I'm also not sure how strong the magnetic field will be, but it might get generated while this clustering and between the gas and this dust, the dynamics are playing between those. So it might happen because there could be a possibility that charged particles might generate and they could
Yeah, so
possibly
some
generate.
conductive field
Yeah.
or whatever. I mean, there will always be probably local field being produced, just like Mars does on a local
Yes.
scale, where you have actually these parts, because the atmosphere of Mars is very small, right? Very tiny. So it doesn't have a natural way of redirecting all these particles that are attacking it from the sun. So what it does, it has some kind of local magnetic fields being produced by the particles bombarding on the surface of Mars.
Okay.
It might be also something like this, some radiative pressure from the star
Yeah.
that pushes particles through the cloud, something. I mean, so complicated, and
Yeah.
that's why I'm also asking this question.
I guess
I mean, I can already answer the question by just a simple no. The approach is not approximating a real cloud collapse well enough.
okay.
But we have to start somewhere.
Yeah.
But I think the more interesting part, of course, is what you say. Indeed, if you do think about these effects,
Yes.
how
Yeah.
important they are, because this is what you
Just
as a researcher want to
to
do,
take
right?
care.
You want to look at these results, or you want to look at these effects, and you want to ask yourself the question: is it important? Do I need to take it into
Yeah,
account?
definitely. Yeah. I mean, this approach would be a like interesting thing to discuss. Like, is it really important, as you said? So
Yeah. So that leads to these back of the envelope estimates and calculations for the time scales, and and even as you say, how would such a magnetic field be produced?
yes,
This is
yeah,
already a good question, a
yeah,
fundamental question
yeah.
in
Already a good
platform.
question. Yeah. How is it produced? Okay.
Yeah,
Yeah. Thanks. Yeah, that's good discussion. Yeah. Thank you very much.
thank you.
Okay, I think the time is up now.
Yeah, I see. So, well, we filled the time pretty nicely then.
Yeah,
At least
yeah,
I did.
we'll,
Sorry about that. So if you have any other questions, you can always approach me on Slack or email, whatever.
okay. So again, thank you very much, Rico, for the nice talk and the nice discussion with the participants. Is there, yeah, photo session? So maybe we will have a photo session now.
Sorry, what do we?
A photo session. So we will take a photo by Zoom actually. So
Is
everyone,
everybody? There. I thought
yeah.
where is everyone? But now they're popping up like. Yeah. Hi guys.
So there's also
Nice to see you.
several person in the seminar room.
Okay, is everyone ready? Has everyone opened their camera? Okay, maybe I'll just start the photo session right now. On my mark, 3, 2, 1. Okay, that's the first slide. And the second, 3, 2, 1. And last, the third, 3, 2, 1. Okay, thank you very much for the photo session. Back to moderator.
Okay.
Okay.
Thank you very much for attending this third day of lecture. So tomorrow you will have a lecture that start in 8 p.m. right? Indonesian time zone. And see you tomorrow and have a good day.
Yeah.
Thank you
you.
guys again for your
Thank you.
attention.
Thank you very much.
Great lecture and great discussion.
Thank you very much.
Thank you very much.
Thank you very much.
See you.
Everyone, have a nice day.
See you.
Bye-bye.
Stay. Bye.